Welcome once again to all the participants and the viewers who are joining us live right now. This is Ali Muzahir as we dive in and start off with the third day of this amazing virtual event, Microfest Plus Plus 2020. But before starting off with one of our very important talk sessions, let me revise today's plan for you all. All right, so right after the talk session, as you can see, we'll have the round two of Mind Zone and of course the CS quiz along with it. And then we'll have the most anticipated moment, the closing ceremony, in which you will all be having talk sessions from important guests. And also, of course, you'll be having your results that who won in all those above modules. Now, let's just begin with our very important talk session planned for today, which will be given by Dr. Taimur Khan, who is a researcher and an academician since 2011 and have a background of professional software development for around 3 years. He is currently serving as an assistant professor in the Department of Computer Science at FAST-NUCES. He also has the charge of coordinatorship for master's degree program. He is teaching to undergraduate and graduate students with particular interests in data analysis, language processing, and network structures. Dr. Khan has published papers in internationally recognized journals and conferences where solutions are and he'll be talking to us about lifelong machine learning with the open world assumption. Over to you, sir.
Thank you. Can you hear me?
Yes, we can, sir.
And you can see my slides as well, right?
Yes, we can.
Okay, thank you. So thanks for the invitation, and it's such a good opportunity to talk to such young and dynamic audience. I am Taimur Khan, and I'm currently serving as an assistant professor in the Department of Computer Science at FAST-NUCES Peshawar campus. And today I'll be talking to you about lifelong machine learning and the open world assumption. So basically, this is moving a step forward from traditional machine learning approaches and considering the fact that what we know as and with what we can train a model is basically not sufficient. And therefore, we need to have a mechanism where a model is going to learn gradually as it move on from one task to another. So before we get started, I would like to briefly elaborate on the traditional machine learning approaches. I know most of you would be familiar, but for those who do not have enough idea, I would just explain it for them that what we mean by a machine learning approach or a model is to have an inductive learning approach where bulk of data is being provided to a model and the model is going to take their data as past instances, and then the model can use that data in order to identify patterns that can help the model to differentiate between the target labels for the data. For example, if we consider this as our past instances, this is going to be provided to the model as the past cases, and the model is going to be constructed that is going to differentiate which emails are spam or not. Now, once the model has differentiated between spam and not spam emails with the help of the data that is being provided over here, it can tackle new instances, and any given data, any new instance that is being provided to the model, it can predict the label of this instance or email as spam or not spam. So that's how machine learning approaches classification or supervised learning in particular works, and that is what we are going to keep as our basic approach. Now, what we talked about was a kind of binary classification approach where we have, if we consider spam and not spam as our classes A and B, so the training data for each of the class is being represented by circles with color. For example, A has got the training data as red circles and B has got the training data as yellow circles, while the instances that has got black color are basically the test instances. So we can see that some of the black instances, that is the test data, are being classified into either class A or B, depending upon their relevance with the training data of each of the classes. Now we can think of this whole classification problem as a line. This is an imaginary line that we can assume that it's differentiating between the data of these two classes, and a point that lies to the right of this line is going to be classified as B because it's more like B as compared to A, while the objects or the test instances that are more like A and are to the left of the line are going to be classified as A. Now, such models are being, in order to test such models, we take the whole data set and we split it into two parts. That is, we
Sir,
have the
your slide.
training data and hello?
Sir, your slides are not moving. Kindly again, if you
Hello?
can share.
Okay. Can you see them now?
You can move it. So you can again share. You can cross it and you can share it.
Okay. Okay, no worries. Can you see them now? Hello? Hello?
Yes, sir, I can see it. You can move it forward.
Okay. Are they changing?
Yeah, it's okay. Good.
Okay. Okay, so what I was saying that we have to train a model on a given data set, and then once the model is being trained to differentiate between certain known classes, we can use that model to make predictions about the unknown instances that we call the test data. Now, we can visualize this process as having two classes represented by the labels A and B, and in this case, we have some training data represented by the yellow circles for representing the class B and red circles for representing class A. The test instances that are represented by black circles are being classified to either A or B depending on their relevance to either of the two classes. Now we can think of this whole process as having an imaginary line between the two classes, where if an instance, that is a test instance, if it falls to the right of this line, it's more closely related to B and is therefore going to be classified into the class B. And if it is on the left of this line, it's going to be more closely related to the training data of class A and is therefore going to be classified as A. So this is how we basically take out the classification process in case we have only two classes. Now, in order to run such experiments, we have already some training data that we call the labeled training data. Now, this training data is separated into two parts called the training data and the test data. We cannot consume all the data for training the model because in that case, we would not know how good the model is. Therefore, we take a chunk out of the data and we keep it aside and do not show it to the model. The model is trained on the remaining part of the data and the test instances are being used for testing the model. Now this slice that was separated from the data set that we have got, we already know the labels for this part. So we can verify how good the model is doing, and therefore we can do all sorts of analysis and we can find its recall, precision, accuracy, and that is going to suggest how good the model is. And in case we have multiple models, we can pick the model that is doing better as compared to the other models for the current scenario. So this approach is a kind of offline or batch analysis where we have a complete data set that is not going to change, and we are using the data set for partially for training the model and the rest of the data from the same data set for testing the model. Now, on this slide, I'm going to slightly drift from what we call the traditional machine learning, and I'm going to present a scenario that why this kind of analysis or this kind of approach for testing a model is not going to be sufficient. So in order to do so, I'm going to consider an online or a real-world analysis approach. If you consider this part, we have data coming from Twitter APIs continuously. So if we think of this data set that has A and B, the model, all the model knows is either A or B. So in that case, if the model is being presented with live data coming from Twitter or any such streaming API, the model is going to classify it to either A or B. So in other words, this model sees the whole world as either A or B, and anything that is coming to it as an unknown instance based on its relevance with either A or B, it's going to be classified accordingly. So you may assume that this model, such a model, is going to make lots of mistakes because it's not considering its understanding of the problem to be limited, and instead it's rather making more wrong decisions with high confidence. Now, I'll pick one such scenario from the 2016 presidential elections in which the candidates were having campaigns throughout the country in the US, and there were many people who were following those agendas and proposals presented by these candidates and were having discussions on them on social media. Now, before the election started, a multi-class classifier was trained with, and it was provided with a number of possible classes that these candidates were going to discuss. And each time a candidate was going to say something, he was going to be rated as positive or negative on each of those categories, like what categories are they discussing and how they are being, and how they positive or negative they are talking about those categories. Now, in the same election, it was encountered that Donald Trump presented a plan for the immigration reforms. Now, this was a particular category that was not assumed to be there, and therefore the model that was trained before the election was not trained for this particular category. And as you would possibly, suggest how the model is going to work in such a scenario is that this category is going to be, all the instances that actually belong to this category are going to be wrongly classified into some other categories based on their relevance. The same way, Hillary Clinton presented a proposal for tax increase. Now that wasn't also part of the multi-class classifier that was already trained. So it means that no matter how much workout we do, we cannot possibly predict all the possible aspects of future. And there are going to be some topics, categories, labels that we cannot think of beforehand. And therefore, we have to be ready for assuming something, or red circles, yellow circles, and blue circles. So these four circles, types of circles, represent training data from 4 different classes. As you can see, we have visualized the imaginary lines that are separating the data of these classes. So we have this line separating the classes or the training data of red circles and yellow circles. But with this, the problem that we are inviting is that these lines are separating the yellow circles, or the class that is represented by the training data as yellow circles, that it has infinite region to this part. The same way, the green circles have got infinite region to its left. And therefore, we are going to make lots of predictions in classification, because we are assuming the whole world to be consisting of all these 4 types of data, and therefore everything that is unseen is going to be classified into one of the 4 possible classes. Now, if we think of this as the test data, so the test data that is actually close to the red circles are being classified as red circles. The same way, the test cases that are more closely related to the yellow circles are classified to the class yellow circles, and same for the other test instances as well. But we have these test instances that are all wrongly classified into red circles. However, they are not represented by, they are not basically part of that class. But the situation that we have over here is that this class is not being represented in the training data, and therefore all its instances are wrongly classified. The same way, we have got some test instances over here, and they are also going to be wrongly classified into blue circles and green circles because they do not have.
Sir, it's again. Sir, it's again there is an issue in. It's not moving forward.
Okay, so where should I start again?
Sir, on from the same from the previous slide, just move forward from the previous slide.
Okay.
Yes.
Okay, what if I just not, if I do not make it full screen? Is it okay like this?
Yes, sir, it's okay.
Okay. So can I start from this slide with the problem scenario?
Yes, sir, or from the problem scenario, yes, sir.
Okay. So what we were talking about is that considering the fact that we have got 4 different classes in our training data, and we have got a model that has to differentiate between the data for these 4 classes. But the test data set may have data belonging to other classes also, for which we do not have training data in our data set. And in that case, these instances that are the test instances, but their labels or their training data is not there in the classifier, and therefore are going to be wrongly classified into one of the possible classes. For example, all this data that seems to be belonging to a different class are going to be classified as blue circles. This training data, this test data is going to be classified into either blue circles or green circles. This test data that's again belong to a different class that the model currently does not know about is going to be classified into red circles because it's more like red circles as compared to the other data, the other classes that we have in our training data. Now, some of the approaches that are being applied in the traditional approaches for tackling with this problem is, one of them is to have a threshold-based approach. So in this case, as we can see that each node in the output layer is going to have some probability for a given class. So if this probability of given class for all the classes is going to be less than a threshold value, we are not going to decide or predict the label for that instance, and therefore that instance is being ignored from the process. So unlike softmax that is going to assign the label for the instance, the label for the class that has got the highest probability, with this approach, if that highest probability is below a certain threshold, we are not going to predict the label for that particular instance. Another possible solution for this kind of problem is to have an extra class label as the garbage class. And now, based on this, an unseen instance can either be classified into one of the known classes or to a garbage class. So everything that is unknown is being represented by this garbage class, and that is going to have the instances that are not part of either of these 3 classes. Now, next, I'm going to talk about some motivation that is going to highlight the possible applications in the real world for this kind of scenario, that why we need to make such open world assumption and why we need to consider that our understanding of the problem scenario or the problem that is being given to us is not sufficient. So one such situation is to have autonomous cars. Now, autonomous cars can be trained for different scenarios, and it can be trained for performing different functions, but we cannot completely consider all possible scenarios that the car may or the autonomous car may face, and therefore can provide training data for it. So therefore, there needs to be an open word assumption that, okay, the model is being trained for 80 or 70 or 90% of the situations, but there may come certain situations that the model may not know about, and therefore it has to make some decision on the spot. And that is going to be very different from what the model already knows. And that has to be coupled with improving the model's understanding of those new instances so that it keeps on getting better at performing those decisions. Another such possible scenario is to have the household robots. Now these robots are assumed actually to be discussing and performing the household activities with people who have purchased them. Such robots can be used in old houses, and therefore how people are going to communicate, they are going to respond. So such models can be trained for certain tasks, that how they are going to communicate in natural language and how they are going to deal with people and interact with them. But there is a lot that it needs to learn once it is deployed on that particular situation in that particular house. Like how many rooms that house has, how many family members their family is having, and what is the nature of each one of them. So if a model could actually have some prior understanding that is helping it to communicate, and then it can build on top of it and learn about the personal traits of each of the members in the family, it's going to perform better and it's going to interact with them in a much more better way. Another such scenario is having commercial conversational agents. These agents are trained to have the business information for any given business, let's say jewelry, and anyone who is interested in getting some information about their particular business, these agents are communicating with them and giving them relevant information. But now this agent, which is being trained for having useful information about like the types of jewelries and their prices, there may be things that this model does not know about, like what is being happening around the world in these days and how that is going to affect jewelry. So if a user is giving such information to such an agent in their conversation and the model learns about them, that is going to help it to communicate with the other users that it's going to have in the next couple of days. So basically what it's doing is that it's using its understanding of the business, and it's also knowing about the current events as they unfold from one to another, and that is basically helping these models to have more meaningful conversations with its. Another such possible scenario. Now, those guests that are visiting the hotel more frequently are going to be recognized by the model, and the model can actually welcome them with their names. But there may also be guests who the model may not know before, and therefore the model needs to have this capability where it learns about new guests at runtime, and then if it sees them the next time, it should be able to recognize them. So what we are actually saying is that we need to consider the open word assumption. And what we mean by the open word assumption is that the model's understanding of the problem is not complete. There are things that we currently do not know about, and we have to admit this fact. Now, once we have admitted this fact, if we again consider over here that the training data is being represented by circles and the test data is represented by triangles, in this case, all the triangles or the test data that is closely related to the training data are being classified correctly. But all the test instances that are different from the training data, the model is actually not making a decision about it, and it's keeping the decision on hold because it does not have enough evidence that what this data or this instance belongs to. So instead of making wrong decisions, it's basically holding on to its decision, and it's not making it unless it has sufficient information to make that decision. Now, a partial solution that is going to solve half of the problem is to have the classes is to replace basically the infinite region behind the training data of each of the classes and is to represent them with rigid circles that tightly enclose the training data. So now if you look into this scenario, in this case, the known classes are represented by the green circles, red circles, yellow circles, and blue circles, while the test instances represented by black circles are classified into one of the known classes if they have enough resemblance with the training data of that class. If that is not the case, that instance is being left as undecided, or the label for that instance is not decided, and we can see these black instances outside of these circles that are not being classified. So what we are doing in the first step is basically we are preventing ourselves from making wrong decisions. And now the next step would be that how we are going to deal with these instances that for which we have kept the decision on hold. So over here, so what we have done so far is that I have identified a problem in the traditional machine learning approach and have suggested that what solution we are going to desire. We haven't discussed how we are going to have this solution, but this would be the desired solution that we would want to have in case of the open world paradigm. Now, leaving that discussion to that point, I'm going to highlight another problem in the traditional machine learning. And that is, if given a task with a data set, the model is going to be trained on that data and it's going to start making decisions about the instances that are related to that data. This type of approach is called single shot learning or isolated learning. The model does not have any memory and therefore it does not accumulate its knowledge and does not carries it from one model to the other. As we can see over here, if we assume that task 1 is to classify between labels A and B, and then we have task 2 that is to classify between labels B and C, the model is going to throw away everything that it has learned from about class B from this task, and it's going to start learning about task B in task 2 from the scratch. So therefore, it's not building on what it already knows and is relearning the same thing over and over again, and therefore it's going to require more data and is going to consume extra computational cost. Now this can be countered with the lifelong machine learning approach, where each time we have a new task supplied by its own data set, the model is going to be trained and it's going to make some predictions. Now, based on the results and the trained model that we have, we can think of something as experience that we can represent in the form of rules. These rules are being fed into a knowledge base, and that is the collective knowledge of the model or a sequence of tasks. Now, the next time the model is going to perform a task, it's going to make a combination of the training data of that task, and it's also going to consider relevant knowledge rules from the knowledge base in order to make a prediction. So in this way, the model is not going to learn about the same thing over and over again. If a model has already learned about something from one of the previous tasks, it's going to improve its understanding of that concept in the current task and is going to build on top of what it already knows. And this is the way that we humans learn, that is to learn continuously. When we see a plane for the first time, we learn that it's an airplane. The next time we see it, we learn about it that it's part of an airline. And then sometime, few months or years later, we learn that there are different flights that they operate in. So each time we see an airplane or we hear something about it, we learn new information about an airplane, and that builds on top of all of the understanding that we already have about airplane. And what I mean by this is that each time we see an airplane, we do not start learning about the airplane from the scratch, that what it is, and instead we build on top of what we already knows. Now, next, I'm going to talk about why this lifelong machine learning approach is useful, why we need to benefit from this. If I have already processed a data set about the mobile phones, that what people are talking about mobile phones and what are the different aspects that people are discussing about these devices. So if the next data set is about laptops, there is going to be considerable overlap between the two devices because they have common aspects like processor, screen, battery, and therefore instead of relearning about these aspects from the scratch, if I build on it and improve my understanding about these tasks or these aspects, that is going to be much more helpful. So different tasks have gray regions or overlapping regions, and therefore we do not need to learn about them each time we encounter them. And in case we can actually build on top of it and have better understanding. And that is the main concept of lifelong machine learning, that keep on accumulating what you already know and build on top of it. Lifelong machine learning has the knowledge cycle that consists of these 4 tasks. In the first task, we learn the new rules. Now, this learning is not the learning that we have in the model, which is basically differentiating or distinguishing between different labels that we have in the training data, but this is rather extracting or generating rules from the data that we have and the way the model is being trained. So what we have done over here is that we have generated some new rules. Then we have given these rules some representation, and the rules that we already have in the knowledge base are going to be maintained over a period of time. Now, this part is also particularly important because if we look over here, we say that the knowledge base is consistently getting new rules out of the experience that we have from the previous tasks. So since this learning mechanism is automatic, we can expect the model to learn wrong rules, and therefore we need to have a mechanism with which we have to modify the rules that we have already learned, and therefore this is what we have been represented by this section, that is rule maintenance, that we are adding new rules after performing each task, but we are also looking into the existing rules, whether they need to be modified or even at sometimes filtered out of the model, because the model can make wrong decisions and can learn wrong concepts as rules. But what we believe is that over a period of time, as it grows in experience, its learning mechanism is going to improve. And then the fourth module is to have the rule transfer, where whenever it sees a relevant scenario, now these rules are from the past cases. So in the current scenario, if it sees that certain rules are going to be of benefit, so it transfers the impact of those rules into that given scenario and benefit from it along with the training data of their task to make better results or good correct decisions. So how we would combine the two, as we said earlier, that we have a partial solution where we have defined these rigid boundaries around the training data of each class, and now we have separated our classification task into a number or a sequence of tasks. So if the model is being trained on these red circles and yellow circles, the model has defined these boundaries around the training data of each of these classes and has classified some of the Blake instances, that is the test cases, as belonging to the yellow class or the red class, and have left some instances out as with their decision on hold because they are not having sufficient relevance with either the red class or the yellow class, and the model does not know to which class they belong. Now, in the next task, the model is being given another classification task where it has to classify between green circles and blue circles, and again the model has done exactly the same thing. But what the point that we need to understand over here is that this data that was previously unknown, we may have relevant training data for this class, and therefore the class that was unknown at some point is going to be known in the future, and the decision of these test instances is kept on hold till that point, and then we can classify all these instances to the class that now we know some point in the future. And the same way as we have resolved the decision of classifying these unknown instances, more and more unknown instances are going to be introduced into the model, and the process is going to continue this way. So what we are doing is that we are not classifying everything based on the current decision that we have, because we are making an assumption that our understanding of the problem is not sufficient. And then we are expecting that maybe what we currently do not know about, that in future there might be a time that we will have sufficient or relevant training data about this particular class, and that would be the point where we can actually classify the data. So in this way, the model is going to learn more and more, and new classes are going to be introduced, and it's going to have to improve its understanding of the given problem. So what we are doing is that we are combining the open world assumption with the lifelong machine learning approach, and that is going to help us to keep on learning and keep on introducing new concepts to our learning paradigm, to our learning problem space. And this is what we call the Matthew effect, or the rich gets richer effect. So to conclude the discussion, traditional machine learning, although it's still a dominant approach, but it's only going to be helpful in scenarios where the nature of the problem is very sensitive and its data is not changing very frequently. But in other cases where we have continuously new concepts being introduced, lifelong machine learning with the open world assumption is going to produce results that are going to be better for scenarios that are continuously changing. But otherwise, this approach, these two are going to be meaningless if we apply it to a single data set and where the data is not changing. In the current world, we cannot expect the data to be changing, to be not changing for most of the scenarios, because we have the big data, IoT that is continuously generating data, we have streaming APIs, and the changing trends, we have different sources that are continuously generating data, and therefore I think the open world assumption is making more and more sense these days than any time in the past, because for any given problem, more and more data is being continuously produced, and that data is evolving, it's trending, and therefore we need to cope up with the changing needs of the data. So that was all about the topic. Thank you very much, and thanks for your patience and listening. If we have any questions, please.
No, sir, there are not much questions. And it's all about today. And thanks so much to have you. And this is all about that. And so all the audience were asking about the NLP, that student of FAST University, of course, about the NLP. That is that using what?
Sorry, I didn't hear the question.
The scope of the scope of you hear me, sir?
Sorry, I couldn't hear you properly, but if the question is there such a yeah, I can hear you now. Sorry again, I can't hear you now. Hello? Hello?
Okay, they are asking that what is the scope of NLP in machine learning?
As you know that the data that we have, it's like most of the data that we are getting is either visual or textual. Although there are some sensors that are generating data in different formats also, but the data that is being collected from the natural sources or from humans is basically of these two types. Either it's visual or it's textual. So therefore, and considering the fact that we have with Web 2.0, we have more people having their textual data has a lot of quite a bigger role to play in the machine learning and in the deep learning and all the latest technologies that are being introduced and to be applied on, and therefore there are actually changing tasks for in NLP tasks like the translations and the classification of different categories. So new concepts are being introduced into NLP also, and therefore the changing machine learning trends and the introduction of new techniques also needs to be applied on these problems. Hello? Hello?
You can hear me, sir?
Yeah.
Thank you so much, sir. Actually, it was a great session and it's so interesting. Thanks to and all the participants, those who have attended it. Thanks, sir, so much.
Thank you.
So guys, today is day 3 of Microfest and the session is end now. And for the schedule, today we will have the CS quiz competition at 6 p.m. Pakistan time. It will end at 7 p.m. And on our competition for the Mind Zone at 6 p.m. It's on the will be start. So there are two competitions today, and after that there will be a closing ceremony at 9 p.m. So all the winners will be announced in the closing ceremony, and there will be our honorable guests and other keynote speakers, those who will be joining us in the closing ceremony. So best of luck to all the participants, those who have participated, and yet those who are going to participate in the competition. See you in the closing ceremony at 9 p.m. today PST time. Thank you.